let me know. Again, if you're having any issues with it, whatever, just let me know. You can have extra time. I think the only thing we're putting a time down on is just try to get it done so you've got a break, basically. You don't have to sort of feed it through the week, but just let me know based on your other commitments. Again, like I mentioned, please watch your file structure. Whenever you mail it in, please do put your name on the actual file of it as well. And I'm looking for the PDF as well as your Copasi files or anything other supporting information that helps you with it as well. Last point, yeah, preference for, if possible, for any of your writing and stuff like that, write it up in a word processor, not by hand, and take a picture if possible. What we're going to finish up today is the last of the temperature effect work. So the goal is to just take you through the last little part of this, talk about how it can be used as far as interrogating reaction mechanisms, and I've got 3 different examples that we're going to kind of work through. So we left off introducing the Arrhenius profile. Remember, Arrhenius versus, I-ring. The Arrhenius versus the I-ring. I-ring actually deconvolutes the delta G double dagger, which pulls us back into sort of normal thermodynamic parameters of your what we call enthalpy and entropy of activation. So this is again talking about the bonds broken or formed as you approach the transition state, and also the entropy changes. Generally, we loosely look at this as degrees of freedom or fragmentation. It's the same way that you guys have probably been using entropy qualitatively before. Of reactions with high entropic changes are ones that have generations of gas, or fragmentation is probably the most one you're familiar with. The reason we set it up this way with this division is it comes back to the Van 't Hoff type plot. You can actually reformat it where we're taking the standard equation, and because this is an exponential series, taking the natural log of it and also breaking out the temperature, you get a plot of ln of kT on your y-axis, 1 over t on the x-axis, and that will get you a linearized form of this for the I-ring equation. 2 parts. The slope helps us to directly access the delta H of this. So you can see just based on the sign of it if this is something that is entropically penalty, plus or minus. But also the intercept part of it gets us back to our enthalpy. And again, we talked about this briefly, but using enthalpy as our sort of a sign of what's happening inside your transition state, the one thing that kind of comes up with this is, okay, you're extrapolating. And more importantly, you're extrapolating back some value. So the entropy that we pull out here from the intercept, remember, intercept here, if you actually look at, since y is your 1 over t axis, we're saying that intercept is where basically temperature is infinite? No, 0, right? No, infinite temperature, that's right, because we're upside down. So the 1 over t value, or y is set up basically is at this exceptionally high temperature, and that becomes a problem when you think about it conceptually. Means we're extrapolating back to a state which is almost impossible, well, it is impossible to actually pull an experimental value to validate. This is extrapolation only. So just even though sort of on its concept, what we're doing is we're saying we're taking data in this particular series, and then we're stretching that out to the solved value of our actual intercept in this position. But really, in practice, the better way to think about it is we're actually going to, especially now, we don't have to rely only on linearization. We don't have to use just that one and extract for y equals 0. You're going to do something more like an exponential fit. So this is just plotting the I-ring parameters where we're just back to rate constant against temperature. So this is the normal sort of data series you would get experimentally, where you would be actually measuring your K rate constant for some series as you walk up the temperature, and this is that normal profile you're going to see. And remember, the only reason linearization was sort of focused on is because, at least in early graphical fitting tools, it was easier. Yeah? Are
these typically done with initial rates?
It's done any way you can, right? Like, we'll talk a little bit about some other points, but typically, remember, you're extracting a K. The easiest way to get a K is by having a known rate. So an initial rate where you extract a K from that part is probably what you would end up doing. But any method that gets you a simple K value could be used, right? It could be a fit value or whatever, but just generally as complexity goes up, it gets harder and harder to interpret your K obs. That's the simple part. So yeah, typically this is probably an initial rate measurement point. But what I want to show on this plot, basically, it's meant to be sort of a confidence interval. If this is the data series that you actually have, and you actually just use your Excel fitting function or any graphical fitting function, you can fit it back to the Eyring equation directly and extract your delta H and delta S directly without having to rely on the linearized form, right? You can actually create a data series that matches the normal exponential series and have a pretty good fit to that data, which in this case, best fit would give you, in this case, minus 8.3 entropy units. What we're trying to show in this is, again, if you're unsure, you can actually go through your data series and add what would a plus or minus 1 entropy unit be, and how does that new data series go? So there's two things that come from that. At low temperature, your error that you're going to get is going to be more tight to your actual data series. So this is something where a plus or minus error of 1 entropy unit down here in this region is going to be harder to distinguish. But as you get to the higher and higher temperatures, you can see that that is a significant enough spit that the amount of error that I could have on my rate constant measurement gets more forgiving, basically. So error blows up as you get to these higher temperatures, which just means trying to nail your K value at some of these very small differences in temperature at that low end may not be the best way to get this. This is something where if you can actually spread out your temperatures over a couple of orders of magnitude, so not just 10 degrees and 20 degrees, if you can get over between 0 and 80 degrees, you'll have a comprehensive data set you can probably trust. So, and that's just, again, to ground you that even on this series here, that error bar of plus or minus 1 entropy unit, you should try to think about that as when we're making these calls of the magnitude that we see of the entropy value, it becomes difficult within this kind of range to distinguish, but we're going to be talking about changes in entropy that are sort of like 6 or 0 versus 15 or 30, right? So these are almost an order of magnitude bigger or smaller as you're actually kind of walking through. So you do have a choice to use either of these two. Just again, reminder that in the Arrhenius equation, you're dealing with your activation energy, which is kind of this more, it's a transition state theory energy value, but it doesn't have a direct relationship back to Gibbs free energy. Your Eyring equation actually kind of grounds in the same energy theory as your delta H and delta S that you've seen from normal Gibbs free energy theory. And they're meant to have the same ideas. In other words, delta H is supposed to be as close as you can, a quantitative sum of new bonds formed and new bonds broken. So it's where energy gets stored or released as you're actually fracturing bonds. And delta S is meant to be sort of a measurement of disorder, right? And again, if you had to restate it, I don't know if at one point in time I got really obsessed with trying to explain entropy and other points. There's some really good YouTube videos from the physicists that talk about entropy as times arrow, right? You know, you can't unmix a stirred pot and stuff because of entropic values. In my best thinking about this, the way I like to try to do it is, remember, it's still that first definition that it's the number of macrostates or microstates in your macrostate, right? It's the number of buckets that you can distribute your energy amount. So entropy goes up if you have more ways to sort of parse out your energy between different points. So it still does come back most of the time for what we're dealing with things like degrees of freedom, so flexibility in your molecule, and numbers of fragments. So just very broadly, this is kind of a good quantitative ranking. If we find a reaction has a negative entropy, negative large entropy, these typically are associated with bimolecular reactions. So what you're doing in there is you've got something where two things are coming together. There's a loss of entropy because you're fusing two fragments together, and generally you're going to get a large negative entropy associated with that. So anything like these alkylation kind of reactions or cycloadditions where two fragments are becoming one, like the Diels-Alder kind of things, typically have these kind of large negative entropy values. So that's one sort of stamp that you can use in place. Again, it does vary. An example up here is this is an epoxide opening reaction of -6. It's close to 0. Does anybody have a theory of why that one kind of lands kind of middling? It's still like a fusion, but
Reduces the strain in the molecule?
yeah, basically you're losing entropy between the two fragments, but you're gaining entropy because you've taken a very rigid structure and made it more flexible now, right? So you've kind of, it's the same thing where this is still looking at an overall. Now again, the one thing you remind yourself about this, these values are meant to be the delta S double dagger. This is the entropy reaching your transition state. So it's again, a ruler that says the correct transition state model that I would be looking at or approaching from this is represented by this entropy value. The other way you could look at sort of a lower value like this -6 might be that argument of sort of early versus late transition state. So in other words, a very large negative entropy like this is pretty indicative of, in the starting state I have two different molecules. In my transition state, it is almost one molecule. It's a very rigid, well-defined transition state with relatively less degrees of freedom. Something like the epoxide, you might look at that as an early transition state where maybe the oxygen, this bond here, actually breaks prior to the transition state. So basically the loss of entropy as you approach this one isn't, you could look at this and say the transition state is still pretty much two molecules. The new bond hasn't really totally formed yet. Yeah.
That would have a different impact if you had like a strong nucleophile for the epoxide opening?
It could. Again, that's one way to, like, what I mean is, even if you know it to be a bimolecular reaction, you're seeing this kind of the size of the negative entropy go from like -6 up to -40. You could interpret that as I have an earlier transition state versus a later transition state approaching a true fusion event versus, well, they're approaching each other. To get over the transition state, it's still pretty much two molecules with a lot of different approach trajectories to allow that to happen, right? That comes back to what we talked about for the A value in the Arrhenius profile. What we're saying is an A value in, let's say, the Arrhenius profile might be something like, for the epoxide, many different trajectories will still lead to ring opening, so it has a certain A value versus something like Diels-Alder. It is really specific. You need orbital overlap in that specific geometry for your homo-lumo parts. There's a very rigid single geometry of a cis-oid diene and things like that. So that's your bimolecular reactions. Unimolecular reactions typically have potentially slightly positive. Now these are fragmentations, right? Where what we're doing is we're breaking part of the molecule off. So loss of a glycosidic bond or formation of a carbocation. This is like your typical SN1 kind of chemistry, or sort of homolytic fragmentation. So these are cases where what we're doing is starting from one molecule and breaking it into two. So obviously positive entropy associated with that. And then unimolecular rearrangements can sort of wander around potentially zero, very low values. But again, it does expand. This has sometimes been interpreted as what's called a compression event. So basically, if I take a molecule like the sigmatropic rearrangements at the bottom, the negative entropy there is generally interpreted to say, I have a molecule which is sort of bopping around. To approach the transition state, it has to kind of freeze itself out, lock into a certain geometry, allow the reaction to happen, and then you go back to rigid again. So there's sort of a compression, or again, there's a certain geometry that's possible, not any geometry that becomes this. This has been applied in certain cases for like pressure-driven reactions. There was actually certain kind of cycloadditions that this kind of prediction predicted that you could get them to go if you put them in a diamond anvil cell, and it does bear out. So if you actually take a reaction like this and put it under high compression, the idea here is that you have a tighter or a more well-defined transition state that you can access with physical pressure, mechanical chemical pressure too. But that's kind of the kind of gateway parts. Where this other one comes in is through a concept of effective molarity. Now you guys probably already know this implicitly. Our reaction where both fragments are in the same molecule is going to be faster or easier. Intramolecular chemistry can be faster than intermolecular chemistry. And this is really just saying that I have a reaction that, let's say, is being done within the same molecule, and I can take the exact same reaction between two. So this would be an example of if I did anhydride formation between a carboxylic acid and an ester, the effective molarity of a system is measured by saying I'll take, let's say, a methyl ester and a carboxylic acid. I'm going to measure the rate of anhydride formation when it's fused together in a molecule like this, or this, or this. Each of these, you'd be measuring the intramolecular chemistry reaction to it. You'd have to come back and then measure the same thing where we basically fragment the two parts, right? So if I did, let's say, like acetate reacting with ethyl acetate or methyl acetate, you'd measure those two effective K values, and then the ratio of the two gives you sort of this bump or a measurement of how fast is the reaction because you're fusing the two pieces together. It was just a quantitative way to look at certain reactions and understand what degree of enhancement you're getting quantitatively just by binding those two things in a fixed geometry. So in the case of the ones in the anhydride formation, we're doing two parts. We're holding the nucleophile and electrophile kind of close in proximity, but also having that double bond in the back restricts all the rotation. We're effectively paying for entropy up front by saying the two fragments can't get away from each other, they can't diffuse, and they're held in a certain geometry. So what you get from this is this ratio of your two K values of the intramolecular versus the intermolecular, and it can be used as an example of acceleration because of that. I pointed out as a structural piece. Does everybody know this kind of trick? If I take, well, so first of all, intramolecular, it's going to be faster than the intermolecular one. But what I've done here is I've taken that center and I've substituted it by a dimethyl, and you can see the rate constant gets a huge bump associated with that. You familiar with this kind of a trick? What are you doing here? Like, what's the impact that we're doing here? We're not changing ring size. By just adding those methyls, what was the outcome?
I think you're just like forcing a certain contour.
Exactly. You're taking a bond, this floppy bond that has sort of free rotation. By putting that gem dimethyl onto it, you're slowing down the rotation for one part, so it's going to adopt certain kinds of eclipsing structures. And second, generally, is it's probably folding back on itself, where you're forcing that floppy chain towards your nucleophile. So you can use, if anybody saw like Will Dichtel's talk recently, most people that do sort of organic materials chemistry use these kind of phenomenon quite often, because it's a way of sort of predictively restricting rotation in certain parts while still having your overall structures available. So this is still a flexible molecule, but you can give yourself, in this case, this is like a 4-order enhancement in your relative rate in the system, which can be used as a programmatic way for things like molecular dyes and molecular mechanics. The other one comes out of this one too. If you guys are familiar with the term Baldwin's rule for ring closing, right? This is just the quantitative assessment from where that one comes from. There's two things you're competing as you change your ring size. One of them, in the red line, this is the entropic penalty that you pay going from the very small rings to the very large rings. So forming a 4-membered ring restricts the molecule a lot more than forming a 16-membered ring. So there's a price that you have to pay for these very small rings, just because you're going from something with flexibility to something that is very rigid, very restricted. On the other side, though, there's a ring strain phenomenon that comes along with it too, where yes, 4-membered rings have both high ring strain, but that's where the combination of the two is what gives organic chemistry the, what was it? We only know how to count to 5 and 6. It's because right there in the sweet spot, that crossing is where you get the 5 versus 6-membered ring is where you get your kinetic bounce from being like, okay, it's a good enough sort of size of a ring where there's not too much ring strain, not too much ring strain to make this thing sort of happen. That 6-membered one is kind of the perfect valley there. So if you actually put the two of them together, what you can get in addition to this from like an SN2, intramolecular SN2, is an effective molarity bump too, which again peaks out where the 5-membered ring is both, the ring strain is not too bad, the entropic penalty is not too bad, and the two species are being held in each other's face in a way that kinetically ends up with this acceleration. So really, it's just, this is the outcome what Baldwin's rules sort of says through has just been pulled out by those three sort of parameters: the entropy penalty that you're going to be putting in, the ring strain that you're forming, but then also the fact that the relative rate that you get by having the intramolecular reaction, just having that restricted geometry, comes out with the 5-membered ring being kinetically favored over the 6, but then thermodynamically the other. So what I'll walk you through is a couple of examples of we can take these linear free energy parameters, temperature effects, all the different pieces to kind of use this in a way of sort of planning or predicting what you might do from a reaction perspective. So this is an example from Melanie Sanford's group, where what she was looking at was this organometallic complex. So it's a palladium intermediate. What she's looking at is she's done an oxidative addition. So you've got this carbon bond to your palladium, and then it's bound by this kind of P-type ligand, where you just have not an X-type ligand interaction to your palladium center. And you have two X-type ligands over here. So this is a palladium-4 complex that was part of her hypervalent or high oxidation state palladium species. What they were trying to figure out was, when this reaction goes through and does that oxygen to aryl bond formation, is it happening exclusively by this intramolecular reaction, where you're getting sort of this square planar, or this complex is actually using this center over here, versus you're getting sort of a dissociation that has to float around in solution, where then the outer sphere sort of attack is coming in. So what they had was an example where two possible mechanisms are being articulated, and they set up a series of experiments to kind of go through and rationally break out each. If it's something like, if this is a good example for you guys to go look up, just because the rationale that she went through and the other parts of it was a good sort of collection of sort of some good inorganic and physical organic chemistry. They went through and did a Hammett measurement where they varied this parameter on your benzoate ring. And you can see that the Hammett parameter here came out as a -1. So think back to Hammett effects. How would you state that, how do you interpret that sort of an outcome? Yes. So that's opposite, right? Like our normal Hammett parameter was electron withdrawing groups make benzoic acid more acidic. So we're saying that having something that balances or stabilizes a negative charge will give us a higher K value. The negative value means you have the reciprocal argument where electron donating groups are helping this reaction, which is opposite the effect of what we saw with the Hammett kind of values. So that's the first part that says, okay, we know that the nucleophilicity of this thing matters. And then we know that it's probably that nucleophilic event is what's actually happening here. This comment here was that for other oxygen to metal bond forming events, it's opposite. So this is specifically saying that for this rate terminator limiting step where you're making this oxygen attack, the more nucleophilic your benzoate species, the better it is for that turnover. So that's consistent in that part. Crossover, they said none. Does anybody know roughly what, if somebody said you tried a crossover reaction, do you know what that might mean here?
Is that when they would deuterate one thing specifically, and you would be able to tell if there's like deuteration on two species or it stays on just itself?
Yeah, or even chemically distinct. So the goal here with what we call a crossover experiment, if we have something where we think this fragment might be the one that's transferring, and let's say that was double. So basically the same X species was twice on the starting material. You end up with a problem of, I don't know if it breaks off, floats around, and attacks, versus the same molecule breaks off, and then that one that didn't move is the one that does the attack. So you have to set something up where you can label those two and know where the starting material came from. So typically a crossover experiment means you would start with this material, and then we would add a different benzoate with a different X group ex situ. And we're saying we're trying to do a competition. We're asking if a molecule starts with, let's say, X equals chlorine in both cases, and then ex situ I dose in just benzoate, sodium benzoate, where X equals, let's say, fluorine. So then I'm trying to see, do I see a product where only the chlorine ends up over here? And then when they say crossover equals none, that's kind of what they're meaning, that they started off with a case where whatever started on your palladium complex is the only benzoate structure that ended up onto your product. The problem with these crossover experiments, unless you can actually interrogate the molecule, we'll see, does anybody see where there could be a problem there? Like the way the experiment was done is I'm going to start with a starting material, which we know has to probably release one benzoate group at least to go forward, but then I'm dosing in an ex situ, an exogenous benzoate group into the mixture to say I'm trying to compete one versus the other. Where could that idea fail? Yeah. Because this is an equilibrium, I could release, if X and X were the same, and let's say this X was something else, there's nothing really saying that I can release it, that one swaps in, and we've effectively scrambled our label, right? And this is the critical part with a lot of, like, crossover experiments are really well defined. They're things that you should definitely use into, but you have to worry about fluxional systems that it's possible that your label is going to actually wash into your system, especially this is where, if we know it's nucleophilic and we know that there's an equilibrium event, there's a possibility you're going to get the label walking. So it's hard to sort of discriminate that and say, well, that was the proof that it had to be this intramolecular system. So the other part that they looked at was that from an I-ring plot, especially in DMSO, it's kind of in and around zero. It looks like it's this kind of ionic reduction or sort of an intramolecular event. There's something going on where we're not seeing a very strong sort of value, where the thinking was, if we're getting a fragmentation as a critical part of this reaction, we should see a different entropy value. So what they ended up doing is using an effective molarity kind of argument. The thought was, if there's two possible pathways we could have, and if we imagine that there's a direct elimination, so basically this molecule on its own can undergo a carbon-oxygen bond formation directly from this structure, then it doesn't really matter how tightly, let's say, that nitrogen center is bonded onto your palladium. Effectively, if we can go directly from the starting material, we're not waiting for the molecule to fragment or open up any open sites. However, if we do something to impact how tightly this nitrogen bonds onto the center, so if it has to go by something where there's a decoordination event first and then reductive elimination, then somehow impacting the ability to form this center would allow us to see a difference in rate. So the one that they engineered is they changed this backbone and they compared the half-life of this complex where there's no bridging structure here, half-life of the structure where we add this bridging structure, and you look at the outcome there, this was a 4-minute half-life. Just by adding that structure over here, we crank up the half-life up to 2.5 hours. So we dramatically slow down the reaction by allowing that nitrogen to bind onto the palladium. This says that it's not going to be a direct elimination process. We have to have a decoordination of that nitrogen-palladium bond to open up a site. So the bottom pathway is the one that ends up being favored by the composite set of data that's through here. Again, this is a light touch on sort of a whole series of different works. But the part I want to point you to this paper is this is sort of, the Sanford group in the end went through a Hammett plot, a kinetic isotope effect plot, a crossover experiment, structure elucidation, and the effective molarity sort of sequence. Taking apart a mechanism like this is this kind of constant back and forth, and it's actually bringing together a whole bunch of different experiments based on the kind of structures that we're talking here. At the end of it, though, most of it is still you're using a rate measurement and a K measurement as your kind of your outcome. Your K in the end becomes the assay that you're using to interrogate your different points. So remember, all the Hammett parameter values that they mentioned through are only possible because you measured 2 different K values and you're actually measuring the ratio, log ratio of those two. Back to the temperature point, though, this was a really, really weird study. And again, I know that there's more of these that are out there, but this was a particularly interesting example. What they were doing is actually a really simple reaction. You're just taking this kind of barbiturate type structure. Remember, those protons there are relatively acidic. You have an isocyanate right here, so you have your nucleophile and electrophile pair. This is really just an enolate generation attacking an isocyanate to install this amide bond. So in the end, you're just trying to form this carbonyl bond across here. Now, the group that was working on this, this was a key intermediate at the very beginning of a process. They were looking at a multi-step continuous flow process. So their thought was, well, if this is the first step that's into it, well, this is just a triethylamine catalyzed reaction. I just have to deprotonate my sort of alkene, the malonate-like system. I'm doing a nucleophilic addition to a pretty decent electrophile. And it's a flow process, which means I want to put as much mass downfield as I can. How hot can I heat this to just get this reaction done? One of the values of having something like a flow reactor is you can take and really work way outside of normal temperatures and pressures. So I can run it at 25 degrees, but if this is in flow, I can print the molecule I need just by holding it at 100 degrees. So they carried out an experiment where they just wanted to simply go through and say, well, what happens if we crank up temperature? The mechanism behind this, if you think of it from a catalytic cycle, it's a really simple catalysis where we're saying triethylamine is going to deprotonate that center to make this guy. So the structure that you'd have there, if you imagine, that's just your enolate. Oh, let's draw it out like this. O minus, and it's triethylamine hydrochloride, or H+. And you've got your 2 points. So what they're referring to is this 1-triethylamine is just the salt form of that. You're bringing in your electrophile, so that's just your isocyanate, NCO. Has anybody played with isocyanates before? Oh, well, you guys are lucky. If you, as a prank, it's Friday the 13th, put an isocyanate in somebody else's shoes, they will never forget it. The smell is next level. If you think thiol smell, isocyanates are so much worse. If you do an addition, then after this, the product addition is just your product enolate, where we just have to get a proton transfer. So after that addition, you've just made new carbon bond, R, and the addition to the isocyanate will give you, let's give it O minus. Or you can draw it as the other resonance isomer, but it's still H-triethylamine. So in the end, very simple proton transfer cycle. Single SN2 type reaction between your carbonyls. It's a nucleophilic acyl substitution kind of sequence. What they found was the rate at 60 degrees, 50 degrees, 62, 100 degrees has exactly the same profile. So no matter what happened, heating the reaction up, passing it through that sequence, they were expecting, remember, rule of thumb is we get a doubling of rate approximately every 10 degrees. So going from 20 degrees to 100 degrees and having absolutely no impact on the rate was really, really weird. They did complete the normal sort of VTNA profile, so they ran a normal sequence. What they're showing here is, here's how the concentration of your starting material 1 varied as your initial concentration of 1 was changed. So it's approximately a first order behavior with reference to this. The isocyanate, the electrophile, again, about a first order behavior, came in at a rate of about an order of about 0.9. And the triethylamine, that's your TCAT kind of measurement, comes in at about 1 as well. So from a VTNA perspective, this seems like a very simple reaction, first order, first order, first order for all components. But again, for a simple cycle like we're showing here, that's not atypical. So there's nothing weird about like a reservoir. It's not like you're forming a complex or there's a catalyst is being tied up in somewhere. The problem that we had here is that the reaction itself is being done through a series of acid-base chemistries, right? So if you imagine taking, let's say, triethylamine and a relatively acidic molecule like your starting material, compound 1, what happens in terms of the temperature if you mix those two things together? If you take an acid and a base, put them together, it gets hot, right? Every acid-base reaction you know is going to be an exothermic type process. So you have to think about each of these equilibria. If I'm starting off with triethylamine, my base, and I add my acid, yes, I'm making this product, but I'm also producing heat while I do that too. So if you think about it in terms of an equilibrium, that first step, heat is a product. And as I heat up the reaction, like I increase the temperature, I'm increasing how much heat is available in the system. I'm actually going to drive that equilibrium the other way. So what really is happening here is in this first step, by increasing the temperature, I'm driving this equilibrium back. And that one can actually be pulled out by what they ended up doing is ln of the equilibrium constant against temperature. This is just a Arrhenius profile. Remember, delta G of any process, delta G equals minus RT ln KEQ. So they could solve the equilibrium constant, the position of the acid-base equilibrium, just for that acid-base equilibrium, and they find out that, yeah, as you heat it up, the equilibrium constant goes down. It drives back to starting material. Likewise, for the product, that's true too, but you can basically go through and say product plus triethylamine, this is just the acid-base equilibrium constant, your Ka. This is the Ka expression for your starting material and base, so these are not the actual cycle. What they're able to do is just measure that equilibrium constant, measure this equilibrium constant, and prove that in both cases, as you increase the temperature, what's happening is, yes, the second reaction, this part right here, is temperature sensitive. It does actually go faster. It follows normal Arrhenius profile. The problem is, we have no more, the concentration of this species here goes down. So that concentration, that intermediate, is dropping lower and lower and lower as you heat up this reaction, even though the cycle after it, the second step, is going faster. So that ends up working like a thermal buffer effectively. So in a good way, this is why certain reactions and certain alkylation reactions work really well at scale, because you actually have a self-regulating effect. If I put this thing together and I was worried that heat produced a product which made the reaction go faster, you end up with a thermal runaway. So running something like this at very high concentration and potentially high temperature becomes a liability. A lot of acid-base chemistry that can look like this is something that you have to worry about, because if it is one of those cases where your rate constant, let's say the turnover limiting step was K2, if we're heating the reaction up and the temperature is increasing, it's going to get faster and faster, which means more heat, which means faster reaction explosion. This is one of those cases where, in fact, a lot of these kind of simple alkylation systems actually behave like this, but it's also, it only really shows up where the second step, that first intermediate, is what's actually your turnover limiting step across this. So that acid-base system is actually what's slowing down the coupling to your isocyanate. And by restricting that concentration at higher temperatures, this is where you're getting this weird buffering effect. So again, just the quick part to there is that there are these examples out there, and it's not always directly, it's not just a simple Arrhenius equation. Sorry, yeah?
So here, in this case,
The overall rate, yeah. Like basically, if you watch the catalytic cycle, the consumption of my starting material or the formation of a product has identical rate for the full catalytic system. Yep.
So is that just a coincidence here, or that the two effects are
Yeah.
exactly opposite?
I think the numbers worked out just perfect. So you're right. The fact that it's identical is a coincidence. The fact that heating a reaction up will not give you a sort of a direct Arrhenius correlation is a general consequence. But you're right. In this case, that it just perfectly balanced where the loss in concentration of 1-triethylamine perfectly matched the increase in your K2 as a pretty close 1-to-1. I don't know if there's the good evidence that has to be general in all cases. I think the other message of that one too, and this is a general part, remember, every reaction is the rate observed is equal to your K times the concentration of something else. What they were trying to do is vary temperature to affect K, but what they were doing is K goes up, concentration goes down, we have a balance, right? And rate just stayed the same. But you're right, the magnitude is the thing that comes out. The last one I want to mention is this paper by Donna Blackman. This is a concept that she came out with recently where the idea is instead of, like if you have to actually go through and build an Arrhenius profile, what we've been saying, especially back to some of the early slides today, we need to measure K at temperature and another one and another one. We actually have to scan a relatively broad set of temperatures in order to fit it to our actual Arrhenius profile or I-ring profile. We need a lot of data, and if every one of those reactions is set up a reaction, do a perfect kinetic measurement, extract a K, do it in triplicate, this is a lot of individual reactions you have to set up. It's a lot of material, and that's basically why most of the time Arrhenius plots are kind of the last thing that you do after you've exhausted every other option, because it's a lot of work. What she got this idea was, if we had a fast enough way to measure the rate of a reaction, so an in situ measurement for what's going on in the system, and I know the rate of some process in some small delta t. So if I measure a very small delta t, I can measure in this space right here the rate of that reaction, which is just my tangent. So this is in this case on the plot that I'm showing you there, we're measuring the rate for this small point right here for some small delta t. And if in that time, I also know for that same time what my temperature was, and I'm going to call it temperature 1. If I'm slowly increasing the temperature over time, I can segment this reaction into a whole bunch of little buckets where each one of them gives me a representation of some rate at temp 2 through some small time interval. So as long as I know how slowly I'm increasing the temperature, if I can measure the rate instantaneously at that particular temperature, and I know those two are well correlated, one reaction actually gives me a whole bunch of little buckets of different temperature experiments. Again, it has to be well behaved. There can't be sort of other temperature effects like a decomposition against that one, but it allows you to take a single reaction and sort of scan it over the entire time course. So this is a CN coupling, a Buchwald CN coupling that she studied pretty much to death in the past. It's an interesting system because depending on which catalyst you have, catalyst 2A shows a profile that looks like this. So at 60 degrees, holding it isothermal, you're getting what looks like a normal first order profile. And in that case, they know the resting state for that catalyst is sitting right here. That's just the free palladium 0 catalyst. For a different ligand or a different nucleophile system, this becomes the resting state. So at 80 degrees with this other catalyst, what you're getting is a resting state of this the complex where we're still waiting for our carbon-nitrogen bond. So the reductive elimination is the resting state for that particular system. I'm only mentioning it because this was just an example of we have two different catalysts where I have two different resting states. That was determined from some other set of experiments by normal VTNA. We found out the resting state by doing a variation of individual components. We can say one of them is waiting for oxidative addition, rate determining step at the beginning. The other one is rating for reductive elimination. So we have two archetypes. What it means, though, is if you look at the overall profile, starting from our catalyst over here. We have a 0 order profile. It's basically just binned up over here, and we're just waiting for that reaction to happen. Concentrations don't matter in this system. We're just have a steady state concentration of that later intermediate. Versus in the blue case, we're dealing with something that the starting material concentration, this guy right here, as it gets used up, you're seeing a decrease in rate. So it's a good prototype for 2 different kinds of systems that also run at different temperatures. So what they did is they took the 2A system and they ran it 3 different times where they're changing the rate at which you're changing temperature. So this is where what I'm going to do is I'll talk you guys through this now. Take a look at this. I'm going to give you guys some Excel sheets so you can kind of put your hands on it, but the data does get a little bit hard to sort of visualize because now what we're talking is not just rate of product formation, we also have a rate of temperature change. So you're looking at this coupling between the two systems. So what you're seeing here is this is rate against time. This is time axis across here. And if I change the rate of heating from 0.1 degree a minute to 0.2 degrees a minute to 0.3 degrees a minute, what you're seeing is these sharper and sharper profiles. So again, implicitly, what we're saying is, on the most extreme one, 0.3 degrees a minute, if I heat the reaction faster, I get to a higher overall rate because I'm getting to a higher temperature in less time. And there's also a case there where, because I'm getting to a higher rate, it's also concentration sensitive. I'm ramping up the reaction to a point where the rate is increasing quickly. Versus if I heat it slowly, I'm getting this more flattened one. Heating it slowly means it takes longer time to get to these higher temperatures, and I'm using up more material as I do that. And then the same profile done for the other chemistry across this. You can then take those individual, these are against time, this is plotting those same ones against temperature. So what you get now is this profile of how does the rate of the reaction vary as a function of temperature regardless of the scanning rate against those points. Basically what we've got here is a whole bunch of individual Arrhenius profiles. That's the Eyring sort of graphs for both of these two. And you can use these to go through and plot them directly onto an Eyring profile where all we're doing is taking those small segmentations and saying, I know the rate at some temperature. I can plot them. In this case, this is just 3 replicates. And what I get is 2 very different Eyring profiles at the top where the slope of those ones are equal to your delta H and the intercept is your entropy. And that just goes back to the last part of her system. In this case, the actual Eyring profiles go back to match some of the experimental data they had, which talks about what the transition state of those two. Effectively, it validates what they said about the mechanism, where the blue curve is a oxidative addition limited system. So you're actually taking a binary event. That means the entropy for that system is going to have to be negative because you're taking 2 things and fusing them together. Versus the pink one, you're starting from one molecule and you're fragmenting it. So that's a case where the entropy is going to be positive. The rate determining step in the purple case is a case where you've got one molecule that's fragmenting it to 2. So this is a thermal profile that matches what the normal VTNA data is, that one of them is a fusion reaction, negative entropy, one of them is a fragmentation reaction, a positive entropy between the 2. And again, done by basically 2 scans instead of what would have been like 60 individual experiments. Difficult to set up. Math is a little bit tricky, but very useful as you kind of move it through. Anyway, have a good break, you guys. I will talk to you guys next week. Actually, week after.